Assalamu alaikum. So let's wait for 2-3 more minutes. देर में मैं आपको एक शेर सुनाता हूँ अपना। दूर तुमसे हो गया हूँ, रास्ते में खो गया हूँ। सुबह थी और जागना था, रत जगा था, सो गया हूँ। So let's now start learning about what we were discussing before. So let me quickly review discrete time Fourier transform. अगर आप लोगों के कोई comments हैं तो you can just keep putting your comments. Discrete time Fourier transform. That's what we were discussing, and before we do that, let me also first discuss a project, or primarily a lab, that relates to coronavirus and its modeling. Modeling of coronavirus. If you remember, we have been talking about two systems. One is a finite impulse response system. The other one is infinite impulse response system. And the simplest infinite impulse response system is y of n is equal to y of n minus 1, a y of n minus 1 plus x of n. Okay? And if you also remember that this a primarily makes this system either a stable system or an unstable system. Okay. Now, and you also, if you remember, the impulse response of this system, h of n, is a n u of n And if you also remember that impulse response is what? Impulse response is input. If you input to a system an impulse at zero, an impulse at zero, okay, means if we are considering coronavirus, it means that just one patient getting into Pakistan, one patient. The coronavirus is primarily can be modeled as a first order infinite impulse response system with a value of a greater than 1. So this is why it is dangerous or scary. For example, if its value is 2, we know it doubles. This is the impulse response. Just one person, then 2 persons, then 4 persons, then 8, then 16, then 32, 64, 128, 256, 500 something, 1000. And very soon, what happens to an unstable system, that it goes to infinity. Okay, it goes to infinity. And this is what we are witnessing almost everywhere. And this is only impulse response. And now what is X? So now let's think about what is so, and this is how we are going to model it. A, Y, n minus 1 plus x of n. So x of n is the input. These are the people who are coming from outside and entering in Pakistan from borders or from flight coming to Karachi, Lahore, Islamabad, So x of n, it's a time series. If you plot this in time series, so this is the first person who entered from somewhere. May it be, some date of January of something. And then like 2 people affected coming into Pakistan, then 1, then 2, 4, 8, 10. So this is x of n. So x of n are the new input to the system. So they are coming in, and whereas yn minus 1 are the people who are already affected, and a basically tells us that how many other people they are affecting. Okay, they may be affecting like every person affecting 2 persons, so it will be doubling, or it may be 1.07. So we need to figure out the value of a for different countries, for Pakistan or for USA, or for if it goes uncontrolled, and we need to somehow just estimate the number of people, affected people entering into Pakistan. Even one person can play havoc, and you can just imagine that if like continuously people are coming in and they are being affected, and then they are then continuously going to affect more people. So if you run this simulation, you will find out that again very soon it touches infinity. Infinity means everybody in Pakistan gets affected in very few days. So this is n. So now n0, n1, n2, n3, n4, n. What should be n? It may be a day, it may be a week. It depends that how we are doing our statistics. Scary. Okay, just one person. One person can just, because one person means the impulse response, and one person play havoc. Now, let's see how can we control it, like what the current government is doing, that you have lockdown. So this is the lockdown model. Lockdown model. Okay, and we are going to do this in our lab. So you can find out number of households in Pakistan from Pakistan Bureau of Statistics website. So that will tell you that how many people are actually, how many households are there, and average number of people. Let's say there are 4 people, 5 people in a household, 6 people in a household, 8. So average number of people in a household. Though still this will be, the model will be the same, which is y of n is equal to a y of n minus 1 plus x of n. But now you will apply it on every household. So this is the people, number of people getting affected, maybe one person getting affected in a household. But the scope of this IIR filter is only limited to a household. So at a max, if one person is affected and he is locked down, he can only affect 6 people, not more. Okay. So while you are running simulation, you can assume that let's say you start with 500 households are being affected, and every household has 5-6 people. So in worst case scenario, okay, you can still contain this virus. So you run the simulation, find out that how can you control the spread of coronavirus by just modeling it as a first order IIR system. Now let's assume that okay, so let's assume that so we are not controlling it to some point, like every country is doing. So they're expanding exponentially, they are somewhere, then they realize that they got to control. Okay. So assuming everybody is being affected, and now you start controlling, or people are being cured, they go to hospitals, and so now this equation will work. Minus x of n. So a has to be now less than 1, because now people are going to the hospital, they are being treated, and they are recovering. So a has to be less than 1, and you see that they are recovering. And what is minus xn? These are the people who are dying. These are the deaths. Okay. So this will not go back to 0, it will just be somewhere. So these are the total number of deaths. So and then so you can always model it in lockdown. If you lock down, what happens? And still this model will work on every household, that people are recovering, and you can apply it on country where you don't take any precautionary measure and people are just getting affected. Now minus sign is because people are dying, they are getting out of the system. So that's the minus sign is for the death. Okay, for example, there are 200 people and A is 0.9. So you cure out of 200, 0.9%, 0.1% you are recovering. So 20 people would recover. So it's like 180 people will still left. Once you multiply 0.9 with 200, you get 180, but 2 die. So left will be 178 for the next iteration. So negative sign is like people are dying, they're getting out of system. And so for the next iteration, the people of recovering still with the same rate, but now out of not 180, but 178 people will be recovering. So N is the death. What is the solution? Because as you know, though even you lock down in the day, you release the constraint, and then even one person, you can still unstabilize the system, because again one input means an infinite impulse response. So the only solution is that you remove lockdown, but you got to find a way to test every person, maybe every day. The best solution. Every day you test. If you find somebody is affected, then he goes in lockdown. So once he goes in lockdown, he is only affecting. Still, it is modeled as a first order IAR filter, but he's only affecting those many people, the number of people who are there in the household. Okay, so what I want you to do is kindly run this simulation and put it on social media. Like, this is, if we don't control, this is what is going to happen. Even a single person with, even if you keep A as 1.09 or 1.1, you will find out that even with this little rate, it goes to infinity. Okay, the number of affecting people, infinity in our case means every person in Pakistan, almost every person in Pakistan gets affected. So lockdown can contain, but it is not a permanent solution. So the permanent solution is that we got to have a test. That tests got to be performed, and we got to perform these tests regularly. Ideally, everybody every day, but if not everybody every day, but we got to make sure that people are being tested, and whenever somebody's result is positive, we need to put him in lockdown in his house, and so that he only affects those many people. So this is the lab. Please just spend time so that you contribute in making people understand the seriousness of this disease, and also making people appreciate that a solution is very, very important, and solution is only that we got to test, and testing is the only solution. So we do this lab, and then I want to see perhaps a table, if you can model, see how good you are modeling. For example, USA. What is the value of A for USA? Okay. What is the value of A for Italy? What is the value of A for Pakistan? Okay. So higher the value, dangerous it is. So you can just do the modeling, figure out, put this in this table so that people understand and appreciate. And as you know, minus x of n is the number of people dying, and this is a recovery equation. Recovery is also modeled as a first order IER system. Okay, so with this, now let's start learning. And you see the value of signal processing as well, that with a little knowledge you can run these simulations, make people understand, put it on your social media, plot your graphs, and put those graphs, making people again understanding. So now let's start learning about discrete time Fourier transform. And as you remember, we said it's a transformation which takes you from time domain to frequency domain. What is frequency domain? It's primarily the number of exponential in the signal. So Fourier transform says that a signal primarily consists of many exponentials, and let me try to adjust. So number of exponentials, and it's always good to see a signal in frequency domain, and I gave you several examples, especially the spectrum. The way the spectrum is being licensed, you find out VHF radio spectrum, and then somewhere you find out your 3G spectrum. And I also mentioned this is the most expensive commodity in the world because of its limitation. Okay, and then somewhere is Wi-Fi. So it's always good to see a signal in frequency domain. But it's just a mathematical expression, a mathematical formula that gives you an indication of the frequency contents in a signal. So, and then we also know mathematicians like that every transformation should have an inverse formula as well, so that you mathematically go in a domain, and then there has to be a provision of you to come back in the same domain. Okay? And so this is, you come back in x of n. So x of exponential j omega is summation n goes from minus infinity to infinity, x of n exponential minus j omega n. Okay, so we know this. Then we started learning about the properties. The properties. And the simplest property is if you delay a signal, a delay, okay? And we know if you delay a signal in time, so primarily let's say a signal has only one frequency. By delaying the signal, we know that you cannot change the frequency, you can only vary the phase. So it's very obvious, trivial to understand this thing. Now this is the phase. If it is a cosine of omega naught n, then this will be cosine of omega naught n plus phi. So that's all you can do to a signal, that you can change its phase. Okay, so mathematically we write it like this. If x has a Fourier transform x exponential j omega, and you delay it in time, so then the new transform is going to be exponential minus j omega d x exponential j omega. See, we also learned about the Fourier transform, which is the most important, and now you also understand, hopefully, that why this is the most important expression in signal processing, the exponential, because it is impulse response of a first order IER system. So this is the most important expression. It is the impulse response of a first order IER system, and we know that we can now use it to model the current scenario. So this is the most important expression. So its Fourier transform, we did this last time, is 1 over 1 minus a exponential minus j omega. Okay. So mostly these transforms are complex numbers because we are finding exponentials, and even a simple cosine, there are two exponentials. So mostly you will end up dealing with complex numbers once you take the transform. So this is the simplest of the Fourier transform, a and u of n. A Fourier transform is 1 over 1 minus a exponential minus j omega. Okay. Let's say if I ask you to find Fourier transform of a of n And this is only if A magnitude is less than 1, because Fourier transform, you can only take Fourier transform of stable systems. Okay, you cannot take Fourier transform of unstable system. Fourier transform only exists of stable systems. So A of n, u of n minus 4. So what is the Fourier transform? First we need to know how to plot this. So you plot A of n, if it is a stable system, it will be something like this, right? Impulses, 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 impulses. And u of n minus 4 is at 4, you have this, a step function, 4, 5, 6. So now if you multiply them together, what you're going to get is, from 4 onward, you get this signal, okay? So this is how you plot A of n, u of n minus 4, right? Now, one way to find out its Fourier transform is that you primarily use the formula, okay? But that may not be a convenient way. Better is that you use the delay property. This is the delay property. Use the delay property. But for the delay property to work, every n has to be n minus nd. Every n has to be with the delay. And here you see this n is with n minus 4. Okay, but this n is not with n minus 4. So what you need to do is you write n minus 4 plus 4 u of n minus 4. So you are not altering the value of the expression. The expression is still the same, but you have now successfully brought n minus 4, n minus 4. So you can now write it as a4 a n minus 4 u n minus 4. So in these type of questions, you need to make sure that you bring with every n there has to be n minus d, and this is a constant, and constant can be you can easily deal with the constant, and we know that. Just you multiply the Fourier transform with the constant, because Fourier transform expression is linear in nature. So now you start like this. You say a of n, u of n, Fourier transform is 1 over 1 minus a exponential minus j omega. Then you say a of n minus 4, u of n minus 4, Fourier transform is 1 over 1 minus a exponential minus j omega into, the property says exponential minus j omega 4. Okay? This is the property which says, okay, if you delay in time, you multiply it by exponential minus j4. Okay? So, but now you need, the expression was this. So you multiply both sides by a4. a4 a n minus 4 u n minus 4 is a4 exponential minus j omega 4 1 minus a exponential minus j omega. And this we know is actually a of n u of n minus 4. So this example tells us that how effectively we can use Fourier transform properties in solving these type of questions in exam and obviously in quizzes. So delay is an important property. Now let's use another property which is important, and that is multiplication. Convolution in time is multiplication in frequency. This is the second important property, is convolution in time is multiplication in frequency. A very important property again, and you can write it like this: x of n convolve with h of n. But if you take Fourier transform, it is x exponential j omega h exponential j omega. Right? If anybody has any question, please feel free to ask. But you must have also studied these topics in your signal course as well. So, फायदा क्या है? Why this property is important? This property is important because you can actually perform convolution instead of using the convolution summation, which says y of n is k goes from minus infinity to infinity, h of k, x of n minus k. And you know all the trouble you take of first plotting h of k, then plotting x of minus k, then flipping x of minus k, then shifting to make it x of n minus k, then multiplying, making another signal, then adding. So going through, all the steps that we started. Using this property, you can just do this by simple multiplication. For example, if I ask you to take Fourier transform to convolve these two signals, okay? This is 0.5 n u of n, and this is 0.9 n u of n, okay? So it's not very simple to convolve these two signals, because you got to first, go through the same steps. Instead of n, write k, then flip one, then drag, and just do all of that, solving summations. But using this property, you can simply find out the Fourier transform of 0.5 n u of n, which is 1 over 1 minus 0.5 exponential minus j omega. Then find out Fourier transform of 0.9 n u of n, which is 1 over 1 minus 0.9 exponential minus j omega. Okay. And then to convolve these two, you multiply them together. This is the fun part. So your y of exponential j omega is product of these two. 1 minus 0.9 exponential minus j omega, 1 minus 5 and 0.9 exponential minus j omega. Okay. But obviously you need to take now the inverse Fourier transform to get back in time. For that you need to perform its partial fraction, and if you remember, I'll not get into performing partial fraction, but I'll assume that it'll be a constant and this and another constant. I hope that you know how to perform partial fraction, but I care less about these constants, but you need to know, and you can change this into x, and then make this 0, put that value here, make this 0, put that value here, so you get the values of the constant. So it's very simple to find out the constants. And then you take the inverse. So inverse is A1 0.5 nu of n plus A2 0.9 nu of n. So this is the answer. So you see, instead of using the summation, you can use this property to perform convolution. Interesting is, let's do another example. Let's say you have a signal, so we are doing another example. You have a signal x of n, okay, and you have another signal and you are asked to convolve these two together. Convolve x of n. One method is the same, that you flip one, then drag and solve the summation. The other is that you take Fourier transform. Okay, and we know the Fourier transform of an impulse delta of n is 1. Okay. It is 1, and if you delay it, the delay property says it is exponential minus j omega. Based on this, the Fourier transform of x of n, is an impulse, so it is 1. A delayed impulse with magnitude 3, so it is 3 exponential minus j omega. A delayed by 2, so if it is delayed by 2, it is amplitude minus 2 exponential minus 2 j omega. Okay. And then is the Fourier transform of h. Similarly, you can easily calculate the Fourier transform of h. It is 2 plus 2 exponential minus j omega minus 4 exponential minus 2 j omega. Okay? So these are the two Fourier transform. It's simple that the amplitude, and location, and you get these exponentials. In order to perform convolution, you do the multiplication. So instead of dealing with exponentials, just to make your life a little easier, you assume that exponential minus j omega is equal to x. Okay? So this becomes 1 plus 3x, minus 2x square, and this becomes 2 plus 2x minus 4x square. And this becomes a class 7 question of multiplying two polynomials. And now if you look closely, you can just directly write this expression that your one signal is 1, 3 and minus 2. So you write this expression 1, 3 and minus 2, and 1 x0 x square. And your second signal is 2, 2 and minus 4. So we write 2, 2x minus 4x square. By just looking at the signals, you can write the two polynomials. And once you have the two polynomials, now you multiply them together. Okay, and we know how to multiply two polynomials together. It is 2 1s the 2, 2 3s the 6x, and minus 4x square. Now with this 2x you multiply, you get 2x plus 6x square minus 4x cube. And with this minus 4 you get minus 4x square minus 4 and 3 minus 12x cube minus 4 minus 2 plus 8x raised to the power 4. So the answer is 2 plus 6x minus 2x square minus 16x cube plus 8x4. And remember, x means just the location. So you can actually plot this. So you plot this, you say it is 2 it is 2, then it is 6, then it is minus 2, then it is minus 16, then it is 8. It is 2, it is 6, it is minus 2, and similarly. So this tells us that a convolution is so simple to perform. It's just your class 7, class 8 questions that you convert it into polynomials, multiply them together. So convolution is primarily multiplication of polynomials. Interestingly, even once you are multiplying polynomials in MATLAB, you can use convolution function to multiply polynomials, and I have done this. So because convolution is basically polynomial multiplications. So these two are the most important properties, though then there are other properties as well, and I have told you the significance already, the significance of a property which says a multiplication is exponential multiplication. Like if you multiply your let me see, 2 plus, मैं इस तरह की गलतियां कर देता हूँ, तो but still let us make sure that we correct it. You're saying कि जी हाँ sorry 8, 2 plus 8, 2 plus 8 बिल्कुल सही है जी. So 2 plus 8 है, ठीक है ना. So 3 2s the 6 आ रहा है, और ये 2 1s the 2, 3 the 6. हाँ अब सही है मेरे ख्याल ये. ओके, अदरवाइज जस्ट आप खुद से चेक कर लें, एंड इफ यू नो जस्ट मेक द नेसेसरी करेक्शन. 6x स्क्वायर, 6x स्क्वायर आना चाहिए. हाँ 6x स्क्वायर कैसे आना चाहिए जी? -8 -4 -4 -8 प्लस 6, तो -2x स्क्वायर आ रहा है. कहीं मैंने गलती की है, अगर की है तो काइंडली करेक्टेड. ओके ओके. So this property is also an important property, exponential j omega naught n x of n. And I told you this is the most important property, especially in communication. And this is the property which primarily is used in all communication systems, physical devices as well. Because what it does is that it pushes the spectrum by frequency omega naught. So expression is like this, that if you multiply something with an exponential j omega naught n, so you get x exponential j omega minus omega naught. Okay, this is what you get. And a very simple example, let's say your signal has only one exponential. You have only one exponential of j omega 1 n. So if you look, the frequency is Fourier transform, you will find an impulse, remember, at omega 1, amplitude 2 pi. So this is what you are going to see. The Fourier transform of this is this, right? So your signal has only one exponential in it. Now you multiply this with another exponential j omega naught n. So obviously, what you are going to get, another exponential which is omega naught plus omega 1 of n. And if you plot its Fourier transform, you will see its Fourier transform will be shifted to this new frequency. Okay? Either Fourier transform shift हो जाएगा, तो और ये भी जो प्रॉपर्टी है ओमेगा माइनस ओमेगा नॉट, primarily it says the same, that whatever spectrum you have will be shifted to a new frequency. And why this is such a critical property? Because remember, all your spectrum, and I've been telling you about the spectrum, that it is the most expensive commodity that exists in the world, is the spectrum, because you license, and like people spend millions of dollars to license a very small part of the spectrum for 3 years, 5 years, 10 years. So our voice or video, these are the two most important signals. Okay, voice and video, these are the two most important signals. If you look at voice spectrum, you will find out voice spectrum will be from 0 to around 21 kilohertz. Okay, but most of it will be somewhere in 1 to 3 kilohertz. So most of the voice spectrum exists here. Okay, sound, maybe the music, because the CD quality music is sampled at about 21 point something, 42 point something, which is twice this frequency. Spectrum is, once you look at a signal in frequency domain, so you find out that how many frequencies the signal has. Like this signal has only one frequency, this signal has just one frequency. But if you look at cosine, cosine will have two frequencies. If you look at voice, voice will have many frequencies in it. But nothing will be beyond 21 kilohertz, our voice. And similarly, if you look at the a video in frequency domain, you will find out it will have around, I think, 3 megahertz. Okay, so kind of these are the this is the spectrum, that the frequency contents in a signal is called frequencies or spectrum. Okay, and why it's important to look at a signal in frequency domain, because only then you understand that how many frequencies, what the band the signal is actually occupying. The band is important. Why the band is important? Because this is what you buy if you want to, let's say, just have an FM channel. So you buy a spectrum which should carry the voice in it. Okay, the voice in it. the voice in it. So all FM channels, 99.9 FM, 100 FM, so they are 200 kilohertz apart. 200 kilohertz apart. And so you buy a channel, and so you got to push your voice or the song which you intend to play to a frequency which you have bought and which you have licensed. So every communication systems comes with almost this, that it takes your voice and multiply it with an exponential, because exponential, instead of exponential, it multiplies with a cosine, and cosine has two exponentials. So the spectrum, you get two copies, one on omega naught side and then the other one is at minus omega naught side. And so the shift. So this is such an important, cosine is such an important component. Then there are companies which only make ICs that can generate a pure cosine, and these ICs are called DSP. Okay, this is discrete or digital frequency synthesizers. So what they do is that you ask it to generate a cosine of any frequency, they'll generate a cosine of any frequency. In your mobile phone, in your radio, in your base stations, in your Wi-Fi, modem, every communication device which is transmitting in air in a band comes with this, which generates a cosine, and it multiplies your signal with a cosine to shift it in frequency in a band which is allocated to you. Okay, so cosine omega naught. So this property is an important property also. Exponential j omega naught n multiplying with a signal will shift the entire spectrum of that signal by that amount. So the shift in frequency is a very, very important property. Then there is another property which says if you flip a signal, and this we also covered, that so a flip in time is flip of the spectrum in frequency. For example, if you have an exponential j omega naught n, if you look at its spectrum is at omega naught, but if you change n to minus n, it becomes exponential minus j omega naught n, so you see the same spectrum but now at minus omega. Okay, I think let's take a break, and we come back after the break. 10 minutes break. Okay, thank you.